Well, welcome everyone. We had a few technical glitches, but we're all on our way now. Welcome to what is, I believe, the 12th edition of Condensed Matter in the City. We're operating this year in a hybrid mode with a small group of us actually together this week in Skye and next week at Imperial College London. So the theme of this year's Condensed Matter in the City is Deep Challenges of Quantum Matter, Insights from Entanglement and Emergence. We're hoping to bring together some aspects from the quantum information aspect of condensed matter physics. One of the things we do in this meeting is we have plenty of times for discussion. And so we've invited our speakers to divide their time up more or less 60-40 between the talk and discussions. And so we will have a lot of discussion. During the actual talks, we'd mainly like to have questions advanced in the chat. And if we think they're important enough, we'll bring them to the attention of the speaker. If you do want to interact with the speaker, please raise your hand first. I think other than that, let me introduce our first speaker of today. As you can see, it's John Chalker from the Physics Department of Oxford University. John is also a senior research fellow at St Hugh's College, Oxford. Over the course of his career, he's made major contributions to localization, the quantum Hall effect, frustrated magnetism, pyrochlore systems, and most recently, he's become very interested in non-equilibrium physics and many-body localization, delocalization, I guess I should say. And that's the topic of his talk today. He's going to talk about many-body delocalization as symmetry breaking. Welcome, John. Thank you for coming.
Okay, thank you, Piers. And thank you to all of the organizers for putting together what looks like a fantastically interesting 2 weeks, of course I'm very glad to be part of it. I feel I should point out that the organizers have made a subtle change to the title of my talk compared with the one that I gave. The one that I gave is what's on this slide, that's to say many-body delocalization as symmetry breaking, and what's on your website is symmetry breaking. It's a bit like the difference between A theory and the theory. So my point will be that there's a certain perspective, which I'll describe to you, from which we believe many-body delocalization is a form of symmetry breaking. But of course, you could say that you choose to take other perspectives, and I can't be confident at the moment that I can find the symmetry breaking ingredient in all other perspectives. But anyway, that will all become clear, I hope, during the course of the talk. So this is recent work with Sam Garratt, who's a graduate student who's just finished in Oxford and will be starting as a postdoc at Berkeley in the fall. And it builds on some work that I did a few years back with Amos Chan and Andrea De Luca. So the outline of what I want to talk about is here. Of course, this meeting is extremely broad. I'm looking forward very much to Paul Camfield's talk as the second talk this afternoon, but it's about as far as you could get from what I'm going to be describing. So I'll begin with a bit of an introduction. But once I've put things in a general context, then I'll zoom in on the specifics of what I want to talk about. And the specifics are that I'll be discussing what are known as Floquet models for many-body quantum dynamics. That's to say, if you use Hamiltonian language, models with Hamiltonians that are periodically time-dependent. And then I'll introduce the language which I want to use to discuss these models, which, with a slight abuse of terminology, I'll call Fundament Paths, what I really mean here is paths that the system follows in Fock space. And in a lot of contexts, as I'll explain, when we discuss quantum mechanics in terms of paths, it's useful to think about contributions in which the phases associated with different paths combine constructively, and this is often known as the diagonal approximation. So I'll talk about the diagonal approximation rather generally, and then the real new content of the work is to talk about the many-body localization transition in terms of the diagonal approximation, and I'll argue that there are domains within the system within which you have pairing between these Feynman paths. And I hope that you'll find these first sections of the talk reasonably intuitive and hand-waving, but I want to finish with a more formal part where I try to ground the things which I've introduced in the first part in terms of a transfer matrix description of the MBL transition. And in that language, I think this claim that we have symmetry breaking has a crisp formulation. And then, of course, I'll end with a summary. So what I'm talking about is one example of a study of a generic quantum system. And over the history of physics since the Second World War, there's been a number of waves of interest in generic quantum systems. So here by generic, I really mean two things. I mean, first of all, we're thinking about systems that have fewer conservation laws than degrees of freedom, so that they're not integrable. And secondly, I'm thinking about highly excited states in these systems so that we don't have some emergent quasi-particle description as is often the case at low energies. And then going through things historically, the first context where people thought about such systems systematically was the context of nuclear physics, where people were trying to understand high-lying resonances in nuclei, and three of those sequences of resonances are shown here with energy running vertically. And the idea was that rather than attempt the impossible and derive a specific sequence from a model Hamiltonian, it's much better to study statistical properties of these sequences, and that led to the development of random matrix theory. And then in the 1980s, people were interested in the quantization of systems whose classical motion is chaotic, such as this billiard with the trajectories of a particle represented by the lines in the picture. And a little later in the 80s, people were interested in mesoscopic conductors. So for example, if you measure the resistance of a conductor that's phase coherent over the whole sample as a function of some external parameter, such as magnetic field, you see irregular variations which may look like noise, but which in fact are reproducible and which can be understood in terms of chaotic motion that's similar to what people are interested in these low-dimensional chaotic systems. So the interest at the moment in spatially extended many-body systems is motivated partly by experiments on cold atoms, but also I think by theoretical developments, and it builds on these earlier steps. So when you go to these many-body systems, of course, various questions pose themselves. So if we have an isolated, truly isolated system, quantum system, then is there a sense in which it can equilibrate? And there's a clear sense in which it doesn't equilibrate, because if we think about the density matrix for the whole system, for example, then if we started off at time 0 in a pure state, we know, of course, that the density matrix remains 1 for a pure state at all later times. But the point is, that's really the wrong aspect to focus on. And if one's interested only in making measurements in some subregion of the system, say subregion A, then it's sufficient to think about the reduced density matrix tracing over the other degrees of freedom. And even though the entire density matrix may describe a pure state, the reduced density matrix in general won't do. And we now have examples where we can do rather detailed calculations showing how the entropy of a subsystem may grow with time and saturate at long times, as one would expect if it had come into equilibrium in some sense with the other degrees of freedom in the system, and the system as a whole had reached a thermal state. Now, many-body localization is important from many points of view, but one way in which it's important in relation to the previous slide about equilibration is that it provides an example of a class of systems which in fact can't act as their own heat path. So if we think about, for instance, spin-a-half chain with some coupling between neighboring spins and some disorder, perhaps involving local fields on the different sites, then we now know that if the coupling between sites is small enough, it has a many-body localized phase. And one way of expressing the properties of that phase is to say that this initial Hamiltonian can be rewritten in terms of some new degrees of freedom, these tors as opposed to the original sigmas. And in terms of these new degrees of freedom, we only need to take account of a commuting set of them, albeit with high order couplings. And the relationship between the original degrees of freedom and these new ones is some local unitary transformation, so that, for instance, if we turn J to 0, then the two things exactly correspond, but for non-zero J, these tors are somehow dress versions of the sigmas. So that's the context that I want to discuss. And the particular model or class of models that I'll be using to discuss it is a class of Floquet quantum circuits. So it's convenient to discuss everything in the time domain. So if we're thinking about a one-dimensional system, I'll think about the lattice arranged in the horizontal direction in this way. And at each lattice site, I have some local degree of freedom, maybe a spin half, or more generally, a Q state spin. And as time goes by, we think of applying local gates which couple nearby sites. So in this example, I couple sites across, say, even bonds in one half step and odd bonds in the next half step, and so on. So that kind of time evolution can be set up in various ways. And what I want to do here is set it up in a periodic way so that the interval between these two dashed lines corresponds to one period of the time evolution, one Floquet period. And then in successive time steps, we apply the same Floquet operator repeatedly. So clearly, choosing to study a system of that kind is partly motivated by simplicity, both theoretical simplicity and also simplicity when one does numerics. But I think it's also possible to make a reasonable case that models of this kind are likely to give us the simplest universality class for many body dynamics. And the point here is that in general, if one can discuss universality classes for many body dynamics, then one of the things that it'll be necessary to take account of is conserved densities. And if you simply think about a Hamiltonian system with a time-independent Hamiltonian, which of course you might view as the simplest choice of all, then with local interactions, you necessarily would have conserved densities. So if we're determined to do without conserved densities, there's actually a positive advantage to going over to a Floquet system. And the specific Floquet system that I'll be showing results for later on is what you could call a kicked random field Heisenberg spin chain. So the Floquet operator for one period is shown here, and the individual two-site gates can be broken down into two parts. One part which couples neighboring spins, and a second part which describes time evolution independently on each site in the presence of fields which are chosen randomly from one site to the next. And as one would expect by now from lots of studies, if the coupling between sites is sufficiently weak, this model has an MBL phase, whereas if the coupling is above a threshold value, it's in a thermal ergodic phase. And so by varying J, we'll be able to go through the MBL to delocalized transition. So there are different ways that you can characterize what's going on in the system, but one of the simplest is just to discuss the spectral properties. So we have an evolution operator, the Floquet operator that I was talking about, which has eigenvalues, of course, on the unit circle. And the simplest way of talking about their distribution is in terms of Fourier components of their density, which are represented by the spectral form factor. So since theta is a periodic variable, t here is an integer, and this simply gives the Fourier transform of the two-point correlation function. And notation, which I'll use a lot, by the way, is I'll write the evolution operator with integer time as an argument, just as another way of denoting an integer power of the Floquet operator. So to get some orientation, we can think about two simple examples. If these eigenphases are completely uncorrelated, then the trace here inside the square is the sum of, well, for n phases, it's the sum of n independent random terms. And so by the central limit theorem, we have a result of order root n, or when we square it, we have a spectral form factor that's n independent of the value of the time variable t. On the other hand, if we draw these phases from a random matrix, and here I'm taking the example of the CUE, circular unitary ensemble, then because of level repulsion, we know that fluctuations in the density of eigenvalues at long wavelengths are suppressed, and the exact behavior that you get, in fact, in that case, is as is shown on this slide. And you'll see that there's a single scale. This time scale is the inverse of the level spacing. If we go from those two toy examples to physical systems, then we can see pretty much similar behavior. If we're in an MBL system, then these eigenphases are only weakly correlated, and we see a spectral form factor that's independent of time, except at very early times. If we go to an ergodic system, then we see a spectral form factor that behaves much as in random matrix theory, except at times earlier than something which, by analogy with terminology in single particle problems, one can call the Thouless time. So it'll be the spectral form factor that I'll use to talk about the many-body delocalization transition. And the other side to the way that I want to talk about the transition is in terms of what I'm calling Fundament Paths here, or more accurately, paths in Fock space. So for instance, if we think about the quantum amplitude to get from some initial state to a final state in t time steps under this Floquet evolution, we can expand that in terms of matrix elements of the Floquet operator, and summing over all of these intermediate states, we can think of as a sum in the usual sort of way over paths in this case, Fock space. And one simple point to emphasize about those paths is that at a given time step, denoted by these labels, of course, we need to specify the state of the system at all sites. So one of these labels for a state in Fock space tells us what the spin orientations are throughout the system. So if we go from quantum amplitudes to probabilities, and for example, ask about the probability to get from some initial state to a final state in a quantum system, then using those ideas as of a sum over paths, we obviously have now a double sum having gone from amplitudes to probabilities, and that's a double sum over amplitudes and their complex conjugates. And it's natural to separate this double sum into some diagonal terms and some off-diagonal ones, because the diagonal terms are necessarily positive, whereas the phases of the off-diagonal ones can fluctuate, and one might hope in various situations that the off-diagonal ones would average out to a small result, or be unimportant for some other reason. So in fact, there's a good history of using that kind of approximation. And it was first developed, I think, in treatments of the semiclassical limit for systems with a few degrees of freedom. So Goodsviller showed how to get the spectrum of a quantum system by thinking about periodic orbits of the corresponding classical system within this diagonal approximation. And Berry showed how level repulsion in random matrix theory, or level repulsion in systems that have chaotic classical motion, can be understood again via this diagonal approximation. And if we go on to disordered conductors, then the understanding that we have of mesoscopics is formally in terms of interacting diffusons and couperons, but these are basically contributions which are captured by the diagonal approximation, and what the theory does is give us a controlled way of putting these fluctuations back in. And then more recently, in the many-body context, there's been a series of works which are looking at using the diagonal approximation in various ways. So firstly, there's been very productive work on random quantum circuits, and one way of expressing why those are tractable is to say that they're constructed so that the diagonal approximation becomes exact after you average over an ensemble of systems. In the context of Floquet systems, both Tomasz Prozan and in work that I've done with Amos Chan and Andrea De Luca, we found limits in which, again, the diagonal approximation is exact. And there's also been work which is, in a way, the direct successor to this early semi-classical work on dynamics, but now in a many-body context, where by taking the semi-classical limit, the diagonal approximation can be justified. So what I want to talk about—
Ask a dumb question. When you've got this discrete time evolution, is there a notion of a classical limit? Wouldn't that normally h bar going to 0 means you've got very, very large phase factors in discrete time evolution. So what would the semi-classical limit be for these systems?
Sure. No, sorry. This work on many-body semi-classics is not for Floquet systems, it's for Hamiltonian systems.
But in the context of your random unitary evolution, discrete, what is the semi-classical limit?
No, I agree that there isn't a semi-classical limit in that case.
Okay, thank you.
Yeah. Okay, so in the simplest case, when we're just talking about the probability to propagate between an initial and final state, there may only be one class of paths to sum over which give constructive interference, but in other situations there can be more, and in general there'll be some symmetry related set of pairs of paths. So if we go to the spectral form factor, which you remember was given by the modular squared of the trace of the Floquet operator raised to the power of the number of time steps, then if I use these blue and green lines to represent the trace of W and its complex conjugate, then we can have constructive interference in the sense of the diagonal terms, not just between paths that start at the same point in W and in W star, but also between pairs of paths with an offset of either 1 time step or 2 time steps or more time steps between their starting points. So in fact, when you take account of that set of symmetry-related pairs of paths, you get an immediate understanding of how it is that the spectral form factor within random matrix theory varies linearly in time. And when we go to a spatially extended system, you can at least imagine, and I'll argue in more detail as I go on over the next couple of slides, that there's a transition as a function of time, and that at least if sites are not too strongly coupled, perhaps at short times each site behaves independently, and then in a system of L sites, each site would contribute a factor of t to the L. Each site would contribute a factor of t to the spectral form factor, and so the spectral form factor for the whole system is t to the power the number of sites, whereas at long times the sites couple together and you return to a spectral form factor linear in t, as one would expect from the diagonal approximation. And to talk about this, I want to introduce some pictorial notation. So I started with this picture of a quantum circuit, but I'm going to be talking now about traces of evolution operators. So it's natural to wrap the circuit into a cylinder. So I can represent the trace of the evolution operator for t time steps by a single cylinder. And if I go to the spectral form factor, then I've got 2 cylinders, one for the evolution operator and one for its complex conjugate. And then what you can imagine happening is that perhaps one of these possible pairings between the paths in W and the ones in W star sets in one spatial region of the system, and a different pairing sets in a different spatial region of the system. And that sets up a kind of analogy between this problem of understanding the spectral form factor and something like a ferromagnetic T-state clock model. So it's a T-state model because there are T possible values for the offset here. And it's ferromagnetic because we can imagine there's some kind of statistical cost when you have domains between different types of pairing. So in the earlier work that I mentioned with Amos Chan and Andrea De Luca, we found a particular large Q limit where you could set up that mapping exactly. And the outcome was partly a tension associated with domain walls between regions with different pairings. And I don't have time to describe details of that, but I'd like to point out a couple of aspects of the results. And the results are to do with the behavior of the spectral form factor at long times as we approach the leading behavior, which is the one expected from random matrix theory, that's to say spectral form factor linear in time. And the corrections come from these domains that I've suggested should exist. And there are a couple of features of the corrections which are interesting. Firstly, if you compare behavior in systems with periodic and open boundary conditions, then with periodic boundary conditions, of course, if you have a domain, you have two domain walls at either end of it. And so domain contributions are more strongly suppressed by this factor of e to the minus 2 epsilon t rather than e to the minus epsilon t in a system with open boundary conditions. And then, of course, you have some entropy associated with the location of the domain walls. And that's these factors of L and L into L minus 1. So you might worry whether these features and the analogy with the clock model is specific to a particular limit where we can set up an exact mapping, but you can also compare with numerics on something with 2 states per site and gates chosen from hard distribution. And what you find are very similar features. So these are plots of the spectral form factor as a function of time. And at long times, we return to this linear behavior. And the deviations from linear behavior are much bigger with open boundary conditions than with periodic boundary conditions. And what's more, the deviations grow with system size in the way that you would expect from the entropy associated with locations of domain walls. So the idea is that from what I've described, we can expect that something like the diagonal approximation holds in these systems, but it does so in a local way. And the paths that contribute to the spectral form factor are predominantly ones with pairing of local degrees of freedom. And that's what we want to probe in more detail as we go on. So if one thinks about probing that, then at a given site in the system, you can think of the state of the spin up or down as a function of time in the path that contributes to the trace of the of W of t. And in the same way, you can think about the state of the spin in the path that contributes to its complex conjugate. And we'd say we had perfect pairing at a given site if the spin sequence in the path that contributes to W is just the same as the one in the path that contributes to W star, except for some shift, which I've denoted here by R. So what I mean by that is that focusing on this particular site, we either have this first situation with zero shift, or the second situation, or the third situation. Or redrawing things in terms of spin orientations, now with time written horizontally, in the path that contributes to W, we have some sequence of up and down spins, and we'd have perfect pairing if we have exactly the same sequence in the path contributing to W star, just with some displacement. So to probe whether this kind of pairing is going on or not, it's convenient to introduce a local order parameter. And the local order parameter is something which has a phase that tells you simply what this shift is, and a magnitude that tells you whether the pairing is perfect, as I've drawn here, or whether in point of fact only some fraction of the spins in the path that contribute to W match the ones in the path that contributes to W star.
John, if I might, this might be a good point to interrupt you. First of all, Sabir had a question on the chat, which I'll invite him to ask you.
Thanks.
Sabir?
In the previous slide, the Haar gates were time dependent or time independent?
Okay. Time independent.
Okay, thanks.
So it was a Floquet system.
Any other questions? Okay, carry on. Yeah.
Okay, so the idea is that we want to introduce a local order parameter that tells us from its magnitude how well the paths match each other, and from its phase what the offset is between the two paths. And formally we can define something like that in this way with some Kronecker deltas and the phase factor that I've talked about and some normalization that's just chosen for convenience. And then the idea is to take this local order parameter and average it. So we average it over the paths that contribute to the spectral form factor, and also we average it over different realizations of our random system. So if we just average the 1-point function of the local order parameter, this quantity by itself, then for the usual reasons, we're guaranteed to get zero because we have no symmetry breaking fields in the model and no symmetry breaking boundary conditions. So what we should do instead, as the simplest object to study, is to look at the 2-point function, and defined in this way, we'll see long-range order in this 2-point function if indeed there is pairing of the kind that I'm talking about. So the central result, in a way, of what I'm talking about is on this slide. So I have this 2-point correlation function evaluated as a function of separation between the 2 points for the 2 phases, a point in the thermal phase and a point in the MBL phase. And over the range of lengths that we have access to, clearly this 2-point function is short-ranged in the MBL phase, and it appears to be long-ranged in the thermal phase. So that's the kind of hand-waving or hopefully intuitive picture of what I'm claiming goes on. And what I want to do in the remaining time is to try and anchor it a bit more formally in some theoretical machinery that we can use to discuss the transition, and that's this transfer matrix.
John,
So,
can I hand a question over to Navinder Singh? Navinder, would you like to ask your question?
Yeah, so could you please go back to the previous slide?
Yes.
Yeah. So my question is, when Mott actually Mott extended the work of Anderson localization, and he introduced the concept of mobility edge. So the idea was that that below this edge you have localized states, and above that edge you have mobile states. So now I was wondering whether in this toy model, is it possible to have such a scenario? So we have only two possibilities here: thermal phase, where the correlation is quite extended, even though the side distance is very large, up to 6. And for in the MBL phase, it goes sharply down, like exponentially down. So is there any intermediate possibility?
Well, it's a peculiarity of Floquet systems, or more generally, I think, localization for unitary operators, that you don't have a mobility edge. So what we have here is a model with a parameter, which is the strength of the coupling between neighboring sites. And if the coupling strength is small, then all of the eigenstates of the Floquet operator are many-body localized. And if the coupling is large, they're all many-body delocalized. We're in an ergodic phase. But the transition happens for the whole spectrum at the same value of J. So it's rather different from what you were describing for Hamiltonian systems.
Yeah, okay, thank you.
Okay. Okay, so I wanted to finish by introducing the transfer matrix way of thinking about things. So that's based on this picture where I have cylinders representing the two traces. And the overall point is that this is a contraction of a tensor network, and we can think either of doing the contraction time slice by time slice, or alternatively space slice by space slice. So if we think of taking the trace of the Floquet operator to the teeth power, we're doing a contraction on a time slice, and if we have a Q-dimensional Hilbert space on L sites, then that trace is of dimension Q to the power L. But on the other hand, if we do a contraction on a space slice, then, well, at each point we have a Q-dimensional trace, and because we need to specify things at integer and half integer time steps, we end up with Q to the power 2t, and then there's another factor of 2 because we've got both trace of W and trace of W star. But either way, we have the option either of thinking in terms of the Floquet operator, or alternatively in terms of a transfer matrix that acts in the spatial direction and generates the spectral form factor. And once we've averaged over an ensemble of disordered systems, then each slice is, after averaging, the same. And so we have a translation invariant transfer matrix here. And in the usual way, the leading eigenvalues of this transfer matrix will be what determine the spectral form factor, at least for long systems. And within that transfer matrix description, there's of course an absolutely standard way in which broken symmetry can be recognized. What we expect is that in a symmetric phase, the leading eigenvalue of the transfer matrix should be unique, but in a broken symmetry phase, there should be a degeneracy between the leading eigenvalues, at least asymptotically, and that will reflect the symmetry breaking. So specifically in this system, what I'm going to argue is the case is that in the MBL phase, there's a unique leading eigenvalue for this transfer matrix. And actually, because we know that the spectral form factor in a large system with sufficiently large values of time goes like Q to the power L, then this leading eigenvalue should just be equal to Q. On the other hand, if we go into the thermal phase, well, if the spectral form factor, as I've said all along, is linear in time in the thermal phase, clearly linear in time independent of L, the only way that that can come about is if the leading eigenvalues of the transfer matrix approach unity at large times. And in order to have the spectral form factor be linear in T, or in fact equal to T, what we need is T-fold degenerate leading eigenvalues. So the final part of the talk is to show you some results from numerics which are aimed at probing this. And those numerics are actually quite challenging because we need to go to reasonably large values of time. And that means, well, firstly, exact diagonalization is certainly no use. And in fact, even Lanczos methods are no use. And what we do instead is look at the scaling with length of the spectral form factor with boundary conditions imposed so as to select particular symmetry sectors in a way that I'll pass over the details of. So what we can do first of all is pick out the leading eigenvalue as a function of time for different values of this parameter, which takes us from the MBL phase to the ergodic phase. And what this shows is that deep in the MBL phase, at late times, the leading eigenvalue is indeed Q, which here is 2, whereas when we go into the ergodic phase, the leading eigenvalue decreases to unity. And then to look at the number of eigenvalues which are degenerate or asymptotically degenerate with the leading one, what we do is look at the ratio of the spectral form factor, which has contributions, of course, from all of the eigenvalues raised to the power L. We look at the ratio of that to the leading eigenvalue. So if there's only a single leading eigenvalue, this ratio is unity. And if there are multiple leading eigenvalues, then this ratio gives you exactly that multiplicity. And again, in the MBL phase, we find this multiplicity is unity. But when we go into the ergodic phase, we find this multiplicity, in fact, is simply T. So taken together, these numerics demonstrate exactly the scenario that I was talking about here. So to summarize, what I've argued is that a version of the diagonal approximation describes the thermal phase. And if we use the diagonal approximation to study the spectral form factor, then that leaves open the possibility of a given path being paired with T partners that have complementary phases. And that pairing is a form of long-range order. And when we go through the MBL transition, then we lose that long-range order. And the reason that I gave my title as the MBL delocalization as symmetry breaking rather than is symmetry breaking is, of course, precisely because this kind of pairing is somehow internal to the theory rather than something which I can tell an experimentalist how to go away and measure. And obviously, one of the things that we're trying to think about at the moment is whether there are ways to go from the physical picture that I've tried to present to measurable quantities which would have similar content. Okay, so thank you very much.
Thank you very much. Okay, so now everything is open for discussion, and I'd like to invite both those who are sitting here in person who'd like to come up and ask a question, and those who are also online to raise their hands. I already see there are 2 questions raised online. So let's start with those. Thomas Vaness, would you like to unmute and ask your question?
Hi, thanks for the talk. When you talk about this local order parameter, how appropriate is it to think about it as local when it has this kind of history baked into it of the evolution that you might expect could see some light cone in the past? And do you have any thoughts about what some sort of field theory might look like for this quantity?
Yeah, I mean, I accept your point that although it's formally local in space, it's not at all local in time. And as you say, that means that it perhaps collects information from neighboring sites. I mean, you can also simply study things which are space and time local. It's just less symmetric, so we didn't do that. Sorry, the other part of your question?
Well, I guess if it's if one is thinking of this quantity being some sort of symmetry breaking phase transition, is there any way to think of some free energy functional?
Oh, sure. Yeah, sorry. Thank you. Yes. Yeah, well, we're trying to do that at the moment. So, I mean, this transfer matrix, it's, if you like, formally an operator on a state of the system on a particular space slice. And that state of the system, well, the system whose state you're talking about there is actually a kind of spin ladder. I mean, it's a ladder because you've got a chain of spins representing the evolution operator and a second chain representing its complex conjugate. And so in that language, this transition is a transition in that spin ladder. Now, the transfer matrix is non-Hermitian, as you might expect, and I think, in fact, necessarily so. So it's some non-Hermitian evolution, but you know, ultimately, yes, you might hope that you could find ways of describing the phase transition via that kind of spin ladder picture.
Thank you.
Good. How about Gennady? Would you like to ask your question?
Yes, thank you. Well, part of my question was already answered by in your previous answer about the eigenvalues, and you mentioned that the eigenvalues can be actually complex, right?
Yes.
So my question is, when you have two eigenvalues which are the same, is you think that it's a sign of a phase transition, but they might be also just complex conjugate. It's kind of modulation transition. Then you have a slightly different story. Did you consider this possibility? That they have just the same models, but they're complex conjugates. So it's basically kind of modulation transition instead of conventional kind of localized, delocalized transition.
Yes. We do understand a certain amount about the general pattern of eigenvalues. It's subleading eigenvalues that we know are complex, and that becomes important in reproducing the late time behavior of the spectral form factor. I guess it seems from the calculations that we've done that the there's quite a lot of structure that I didn't talk about in terms of symmetry sectors of this transfer matrix. And I think the leading eigenvalue in each symmetry sector is real.
Okay. But
Yep. Andrew Green has a question here.
Just a quick question, John. Could you comment on how this relates to the different entanglement structure of eigenstates in the MBL phase and the thermal phase?
Yes, so going in the opposite direction, it's certainly possible to make that connection. So, of course, you can manipulate these expressions for the two-point correlator and rewrite them in terms of properties of eigenstates. And when you do that, you can understand precisely because of the different entanglement properties in the two phases, how it comes about that you have these two types of behavior for the two-point function.
I mean, one vaguely thinks when you talk about these degeneracies in the transfer matrix, and one might have thought that leads to, I guess, sort of cat states as part of these, a cat state structure in these eigenstates. Is there a relationship as direct as that, or is
no? I don't think it's as direct a relationship as that. And the point is that quite a lot goes on by the time you get to the transfer matrix, because this transfer matrix is averaged over the ensemble of systems. And so at that stage, you're no longer talking about individual eigenstates in a particular realization.
I see. Okay, great. Thank you very much. Thanks, John.
Thanks.
Yep. Claudio Castelnuovo would like to ask a question.
Hi, John. Thank you very much for the very nice talk. I have a bit of a far-fetched idea, but if this symmetry breaking scenario were to hold generically, I was wondering if you think there was a possibility of thinking about it in terms of L bits not having just the same axis necessarily, but having generic axis and being a ferromagnetic transition, symmetry breaking, where they become primarily aligned and therefore essentially classical and MBL across the transition. Or if you thought about this at all, or is it too far-fetched?
But it would be the ergodic phase that should be ordered.
Okay, yeah, you would go the other way. Yes, that's right. Thank you.
Let me ask a question. As a complete novice to this whole area, it seems very counterintuitive to ascribe to all the states that we know so well, the thermal states, a state of long-range order, and yet to ascribe to the very rare states that are so hard to produce outside one dimension as being disordered. Did you think of the possibility of some kind of duality transformation so that you could reverse things and describe the many-body localized state as the state of long-range order?
Well, I mean, certainly that sounds a very interesting direction, but I don't think, I don't have any way of following it. I mean, I suppose there is a sense in which, as a function of time, you think of the MBL phase as having obviously indefinite memory. And so in that sense, the MBL phase maybe, yeah, would do the kind of thing that you want. But I'm not sure I have anything very useful to say there. Sabir has a question, I see.
Go ahead.
Yeah, so you mentioned it was some kind of, you can map the system onto a spin ladder. So if I understand correctly, it's a T-state spin ladder, where T is the time, is that correct?
Yeah, that's correct. I mean, strictly it's 2T because, well, sorry, it's a 2T site spin ladder, and each spin is spin a half if the original problem is spin a half.
Oh, I see. It's a 2T, it's in the horizontal direction. But the long range order is in the spatial direction. Where did the spatial direction go? Then?
Yeah, so the long range order is in the spatial direction. I mean, so the spatial direction becomes like imaginary time.
Mm-hmm. Okay. I see. I guess a related question is, is taking the limit t going to infinity somehow similar to continuous time system, non-Floquet systems, and what happens in that limit? Or you can't extend this to non-Floquet systems?
Well, we're thinking at the moment about how to extend it to non-Floquet systems. But it's more than it requires more than just taking very large t. I mean, because if you start with a Floquet system, then necessarily you have the possibility of pumping in quanta of energy at each time step, and so you need to make the time step smoother whilst you take the limit.
Okay, thanks.
Okay, well, can you, actually, there aren't too many questions at the moment, but let me ask you a question. Can you give us a sense of what sort of experimental directions you are thinking about as how you might be able to detect or look at consequences of this long range order?
Okay, well, there's one possibility which I could have put on slides. It's in the paper, but I didn't, so I'll have to try to describe it in words. Which involves, well, I mean, so to back up a bit, I talked about correlation functions, and a natural counterpart would be to discuss susceptibilities. And so something that you could do would be to start with the type of Floquet system I described, and then modulate with twice the period of the original system, and ask how quickly those modulations as a function of increasing amplitude affected the behavior of the system. And essentially this kind of symmetry breaking means that you would expect in the ergodic phase that those modulations would have a much bigger effect than in the MBL phase. And in a kind of similar way, if you modulate at one point in the system, in the ergodic phase, those modulations should affect the whole system, whereas in the MBL phase, they'll just have local effects.
I see.
So I think it's that kind of thing that one should think about.
Very nice. Okay, great. Gunnar Muller has a question.
Yeah, I'll just ask it here with the risk of getting a feedback, because we now have two mics in the room. Yeah, so you get this very nice transfer matrix formalism when you consider this problem of MBL in 1D. But we know that tensor networks also generalize nicely to higher dimensions. So have you thought about whether this is still possible to do in 2D systems? And if so, what the challenges would be, and if it's doable, I mean, conceptually.
Yeah, so conceptually it certainly works. And I mentioned that there was a particular model in work with Amos Chan and Andrea De Luca, where we take a large number of states per site and have a mapping that becomes exact to a clock model. And that all goes through in arbitrary spatial dimension. If you want to extend the things I talked about today, then the obstacle obviously is that it's extraordinarily hard to do numerics to check your ideas outside of one dimension. But in principle, I don't see any reason why this kind of thing shouldn't go through.
Well, any other questions, any discussion that people would like to bring in here? Oh, okay, cool. Come up here because it works much easier than if you.
Hello, John. Thank you for a fascinating talk. I wondered if I could ask, I mean, clearly there's some rather interestingly drastic rearrangement of the eigenvalues of this transfer matrix as we go between the two phases. And what can be said about its properties precisely at the transition and finite size scaling and this kind of thing?
Well, what we've said so far is that we leave that for future work. I mean, what we wanted to try to do was to bolt down the behavior in the two phases either side before looking at the critical behavior. I mean, you know, if you want to fantasize, then, or if someone wants to fantasize, then the question would be whether this is going to be a particularly effective way of studying the MBL transition, and somehow whether it might liberate us from the difficulties that are faced by exact diagonalization and so on. And probably the answer is that there's a conservation of difficulty, and that given certain numerical resources, you know, this will face the same obstacles that exact diagonalization faces as well. But certainly that would be a direction to try to do more on. I mean, if I go back one slide, you kind of see the obstacles here, that in the ergodic phase, you have to go to large times to see the asymptotic behavior. And as you get close to the transition, that time scale that you have to go to see the asymptotic behavior gets longer and longer. So, you know, as always, there's some crossover regime, and it's a question of, perhaps it's a question of whether, you know, whether it's possible to analyze that better than the data from other types of calculation.
Thank you.
Okay, so we're probably drawing to an end, but since you mentioned fantasy, let me ask you a question about fantasy. Could you, we know that glassy behavior can sometimes occur in systems without disorder. So do you think that many body localization or some relative of it is necessarily linked to disordered systems? Or could it be something that might develop under some conditions spontaneously in systems that aren't heavily disordered?
Well, I mean, there has been quite a lot of work looking at that kind of thing. I mean, for instance, Lev Yoffe and Boris Altshuler thinking about coupled Josephson junctions. And I suppose the question is whether you actually have real localization or just very slow dynamics without the quench disorder. And I'm not aware of a context where it's really been established that quench disorder is unnecessary, but certainly it's been shown that you can get very slow dynamics.
What about in the reverse situation of experiments? Would many body localization manifest itself as entropy density no longer diffusing?
Well, yes, I suppose so. What system do you have in mind?
Well, I don't know. In a number of systems I know where you can see linear specific heat and you can't measure a thermal conductivity. It's crossed one's mind. We're talking about fantasy now. Paul Canfield has just raised his hand. Maybe he's got a suggestion.
Sure. Can you hear me, Piers?
Yeah, thank you.
To answer your last question, glass, of course, has a linear specific heat from the disorder. But one of the things I want to point out is you keep talking about disorder. Remember, quasicrystals are highly ordered, but just aperiodic, and they can manifest a lot of these phenomena. So you may want to think about those, having highly ordered, but aperiodic systems. Just as we start entering into experiment, that's one of the phase spaces that this may play into a little bit.
Yeah, and it's worth saying that some of the main cold atom experiments on MBL, in fact, use quasi-periodic potentials rather than genuinely disordered ones.
Okay. I think this is a very good point for us to break. Unless someone has a burning question they'd like to raise, let us end this part of this afternoon session by giving John a great hand. It's been a wonderful talk, very stimulating. And we will reconvene. The next talk is actually in 40 minutes time. That means that, did I get that right? At 4 o'clock our local time here in the UK. I will open up we'll be testing the talk a few minutes before that, but that means we've got at least a half-hour break now. Thank you, everyone.
Hey, Piers, can I test it right now while I have you here?
Yes, thank you. Do go ahead.
Could you share the screen with me then? Or let me share the screen?
Yeah, I think, hang on a second. Let me just make you a host. Make you a co-host. There you go. You should be able to share the screen now.
All right, let's give that a try. So you can see that?
Beautiful.
All right, good. Then I will stop sharing. And I think I'm more or less ready